A point source S of monochromatic light is located on the bottom of a swimming pool filled with water to a depth of 1 meter as shown above. The index of refraction of water is 1.33 for this light. Point P is located on the surface of the water directly above the light source. A person floats motionless on a raft so that the surface of the water is undisturbed. A bit. Determine the velocity of the source's light in water. B. On the diagram above, draw the approximate path of a ray of light from the sources to the eye of the person. It is not necessary to calculate any angles. C. Determine the critical angle for the air-water interface. Next question. Suppose that a converging lens with focal length 10 centimeters in water is placed 20 centimeters above the light source as shown in the diagram below. An image of the light source is formed by the lens. D bit. Calculate the position of the image with respect to the bottom of the pool. E bit. If instead the pool were filled with a material with a different index of refraction, describe the effect, if any, on the image and its position in each of the following cases. Case 1. The index of refraction of the material is equal to that of the lens. Case 2. The index of refraction of the material is greater than that of water but less than that of lens. So, this question is based on a phenomenon called refraction of light. Let us see what is the refraction of light. Here I will explain what is refraction of light and then we will answer those questions. The light is an electromagnetic wave and then light is a form of energy. And then the third one is I am talking about the characteristics of light. So one of the characteristics is light travels in straight lines in a given medium. Whatever may be the medium, it travels in straight lines. And its velocity in vacuum is 3 times 10 to the power of 8 meters per second. This is the velocity of light in vacuum. This is the absolute speed of light. Suppose if it travels in a medium, maybe light, air or water. Light travels through air, light travels through water, glass, and through diamond and any of the transparent materials like oil, etc. So when it is traveling through this medium, the speed changes depending upon the optical density of the medium. Optical density is the measure to which extent the light ray slows down. Okay, so whenever the light ray, and moreover, as I told you, light is an electromagnetic wave. It doesn't require any medium to travel. That means it travels through vacuum also. For example, sound cannot travel through vacuum, but light can travel through vacuum. Remember. Now, let us see what happens if the light travels one medium to another medium. That means, that, for example, if we take, the earth receives the light energy from the sun. Am I right? From sun it is traveling through the vacuum and then through the atmosphere and then it reaches the surface of the earth. So when it is traveling through the vacuum and through the atmosphere contains many gases and then dust particles, etc. No? So what happens to the light ray? Okay, so one such case we are seeing here. So here the light ray is traveling through the vacuum. So see here it is the straight line and then the arrowhead represents the direction of light and then this is called the incident ray. This is called incident ray and then it is striking the interface and this is and just now from the vacuum it is entering into the atmosphere. Okay, so this is the interface between the vacuum and the medium. And then at the interface, the light ray slows down. because this is the vacuum, it's the absolute value, and then it has to travel through the medium. That means the medium has some constraints. So that is why it can't travel with that much of speed. Okay, that means it is just like a vehicle traveling on a highway, and another one is traveling through the countryside. Maybe the roads may not be that much good, or there may be traffic. So the vehicle has to slow down. The same way, the light ray has to slow down when it is traveling through the medium. So because of the slowing of the light ray, it has to deviate its path. That means, remember one more thing, light always tries to travel through the least possible distance. That means it tries to reach the destination as fast as possible. Okay, so just like human beings. So it will find a path through which it can travel faster. Okay, so that is why it tries to deviate from its original path. In this deviation, if we draw a normal to the interface, it bends towards the normal if it is traveling from optically rarer medium to optically denser medium. Understood? Whenever the light ray travels from optically rarer medium to the optically denser medium, it deviates from its original path, and moreover, it bends towards the normal. Okay, this phenomenon is called refraction. Why the refraction is taking place? Because the light ray has to slow down in that particular medium. Okay, from one medium to another medium, when it is traveling, the speed will be different. So let us consider V be the velocity in the medium. Any medium. I'm not saying specific medium. Velocity of the velocity in the medium. Whatever medium it may be, it may be water, or it may be glass, or it may be diamond, like this. Okay. Velocity in the medium is always less than velocity in vacuum, or it depends on the optical density of the medium. So if the velocity is less, it deviates towards the normal. Suppose if the velocity is more, it deviates away from the norm, or bends away from the norm. Understood? So this angle is the angle which the incident ray makes with the normal is called angle of incidence. And then the angle which the refracted ray makes with the normal is called the angle of refraction. And then this ray which undergoes the refraction is called the refracted ray. So incident ray, the ray which strikes the interface is called the incident ray. And then the ray which undergoes the refraction is called the refracted ray. And the angle made by the incident ray with the normal is called angle of incidence. And the angle made by the refracted ray with the normal is called angle of refraction. Okay. Suppose if the light ray travels from optically rarer medium to the optically denser medium, because the light ray has to slow down, because of that slowing, the angle of refraction is less than angle of incidence. That you can make out with the picture. Understood? So this is first one. Next, you will get a doubt. What happens to the light ray if it is traveling from optically denser medium to the optically rarer medium? Reverse phenomenon. See here, for that I put the same thing. Here, the light ray is traveling from optically denser medium to optically rarer medium. Okay, so that is why the angle of incidence is less than angle of refraction. Can you make out? This is the incident ray, this is the refracted ray, this is the normal drawn to the interface, and then this is the denser medium, this is the rarer medium. The light ray is traveling from denser medium to rarer medium. That is why the angle of incidence is less than angle of refraction. But whereas in this case, the angle of incidence is greater than angle of refraction. See here, both the pictures are here. You can compare and then learn. Okay. Now I get a doubt. Suppose if I increase the angle of incidence, what happens to the angle of refraction? The light ray is traveling from denser medium to rarer medium. As the light ray is traveling from denser medium to rarer medium, it deviates away from the normal. Okay, it bends away from the norm. So if I start moving this ray upwards, this ray moves downwards. Am I right? That means as the angle of incidence increases, the angle of refraction also increases. As I increases, R also increases. Till what extent the R increases? If I keep on increasing the angle of incidence, will the angle of refraction also increase? No, there is a limitation. What is that limitation? Suppose if I keep on increasing angle of incidence at a particular angle called the critical angle, the refracted ray just grazes the surface. Understood? That means the angle of refraction becomes 90 degrees. Here, the light ray is traveling from optically denser medium to optically rarer medium. And then if I keep on increase the angle of incidence, the angle of refraction increases, but I can't increase it indefinitely. There is a particular specific incidence, angle of incidence. That means for a given media, here I am taking the air water because the question is based on air water. I am taking that only. So water air interface. For this one, if the angle, the incident ray increases, for any medium, this is the general theory is same. Okay. So when the light ray is traveling from optically denser medium to optically rarer medium, and if I keep on increase the angle of incidence, the angle of refraction increases up to a particular extent, and after that, we can't do that one. Okay. At a particular angle of incidence, that means the critical value. For a particular angle of incidence, the refracted ray just grazes the surface. That means the angle of refraction becomes 90 degrees. So this angle, he is asking us to find out the critical angle. Okay, that is why I said this one. Now the question arises. Then suppose if I increase the angle of incidence further, what happens to the refracted ray? Simple. The refraction no longer takes place because over, no? 90 degrees over. Where will the light ray go? It will enters back to the same medium. So 90 degrees are over and I still increased the light incident ray. That means I is greater. Now I is greater than IC. Okay. So beyond the critical angle, if I increase the angle of incidence, then no longer refraction takes place. Instead, reflection takes place. That means the light ray bounces back to the same surface, same medium. Okay. So this is the reflection of the light ray. It is not the refraction, it is the reflection. And then the light ray, this is normal reflection. No difference at all between the normal reflection and this one. So this reflected ray obeys all the laws of reflection. Okay. That means angle of incidence is equal to angle of reflection. Okay. And then the incident ray, reflected ray, and normal drawn to the surface will all lie in the same plane. These are the laws of reflection. The incident ray and the reflected ray obey the laws of reflection. Only thing is here, the refraction will not take place, only reflection takes place. It is called total internal reflection. Why it is called total internal reflection? There is no partial reflection and partial refraction. The entire light ray gets reflected. No, refraction, forget about the refraction. Okay. That is why it is total. And then why internal coming back to the same medium. That is why internal. Internally getting reflected. That is why it is called internal. Total internal reflection. Understood? Okay. Now, on what other factors the refractive index or the refraction depends? One I told the optical density of the medium. Another one is the wavelength of the light. White light contains many wavelengths. For example, if you know that white light contains 7 different colors. When the white light falls on the prism, we will see 7 different colors emerging from the prism. Why it is happening? Because of the refraction. Here, when the white light falls on the prism, refraction takes place. And white light contains 7 different colors. Each color has a different wavelength. That is why each color deviates away from the normal or towards the normal. Here it is the light rays traveling from rarer medium to denser medium. That is why it deviates towards the normal, not away from the normal, towards the normal. Okay, the bending is towards the normal. But this deviation or bending is different for different colors. That means different wavelengths. Okay, and then how it depends. So the refractive index is proportional to the 1 by wavelength, or refractive index is inversely proportional to the wavelength. N is inversely proportional to wavelength. N is the refractive index and lambda is the wavelength. Okay, that means lesser the wavelength, greater the refractive index. Am I right? If lambda is less, N is more. If lambda is more, N is less. So if you take the lambda of two different colors, that means violet and red, two extreme colors. Lambda of violet, that means wavelength of the violet is 380 nanometers, whereas the wavelength of the red is 700 nanometers. So which one will, which one has the more refractive index? Obviously, the lesser one has no. So violet has more refractive index than the red. Violet has higher refractive index than red, and then the bending is more. Violet will deviate more compared to the red. Understood this one? Okay. And then one more thing is, what is the relation between the refractive index and the angle? We are saying that the angle, no, angle I and angle R, that a scientist called Snell gave the relationship. So here, if you see this one, I is the angle of incidence and R is the angle of refraction, and N1 is the refractive index of the first medium, and N2 is the refractive index of the second medium. So N1 sin theta, N1 sin I is equal to N2 sin R, or sin I by sin R is equal to N2 by N1. That means the ratio of the sine of angle of incidence to the sine of angle of refraction is a constant. That is the Snell's law. Got it? So N1 is the refractive. That means here the light ray is traveling from one medium to another medium. Okay, that may be whatever it may be. Here he is saying that the light ray is traveling from water to air. So N1 is in this case N1 is the water. This is water, and then this is air. And remember, for air, the refractive index is, for air, refractive index is 1. Okay. Now, based on this, this is the basic information you need to solve the question. Okay. Now, let us go back and then solve the problem. Let us write the answer for the question. So the first question, he is asking us to determine the velocity of source in water. Okay. So use the relation n is equal to c by v. Just now I told no, n is equal to c by v. So using this equation, we can easily find out the velocity of light in water. C we know, c value, absolute value, we know 3 times 10 to the power of 8 meters per second. And then n value is given to us. Here he gave a 1.33. So put 1.33. Solve v is equal to 2.3 times 10 to the power of 8. Got the answer. And then the next, what is he is asking us to draw the diagram. So how the light ray is traveling? Light ray is traveling from optically denser medium to optically rarer medium, water to air. So angle of incidence must be less than angle of refraction. The refraction is taking place here. So draw the interface and then draw the line. Here you are seeing, I is less than, if you want, you can put I is less than R. Angle I is less than angle R over. Third bit, we have to find out the critical angle. To find out the critical angle of the air-water interface, we use the Snell's law. N1 sin I is equal to N2 sin R. So here I is the IC critical angle, because he is asking us to find out the critical angle. So when I is equal to IC and then R is equal to 90 degrees, am I right? And then here it is traveling from water to air. So air refractive index is 1, we know. And then sin 90 is equal to 1. Am I right? So the right hand side becomes 1. And here we have to find out IC. IC is equal to 1 by 1.33, or IC is equal to sine inverse of this value. From that we will get the value. Okay, that is the answer for that one. And then the next bit. What is the next bit? Yeah. Now, he put a lens here, and then from the source, the light is coming. And then from the lens, we have to find out the distance of the image. Okay. So for that, we will use the equation, no, lens equation we have, no, 1 by f is equal to 1 by d naught plus 1 by di. So f value he gave as the 10 centimeters and d naught is given as 20 centimeters. We will calculate di. So di is equal to 20 centimeters. So just a substitution of the values and we get the 20 centimeters. But here the twist is he's asking us to calculate the position of the image with respect to the bottom of the pool. So the bottom is at 20 centimeters. The lens is 20 centimeters above the bottom. Okay. So see here, this is the bottom of the pool. So the image distance is 20 centimeters from the lens and then from the bottom another 20 centimeters. So 40 centimeters from the bottom of the pool. Okay. So that you should remember. And then next one, uh, what he is saying is instead of water, he filled the pool with a material whose refractive index is same as the refractive index of the material of the lens. So what happens if the entire thing is filled with the same medium, the lens, and then the surroundings are of the same medium, the refraction will not take place. So when the refraction will not take place, image will not be formed. That is the answer for the first case. Okay, and then the next case. In the next case, what he did, he filled the pool with a material whose refractive index is greater than water but less than the refractive index of the material of the lens. Now, what happens here? You see this one. So, um, N fluid is less than N lens but greater than water. Okay, so we have to calculate the relative refractive index. So to make you understand, I put some numbers. For example, if the refractive index of the material of lens is 1.5 and then water he gave as 1.33. Suppose if the fluid we take greater than water and less than lens as 1.4, what is the relative refractive index? It is in the first case it is 0.7 and in the second case it is 0.1. Okay, so lesser the difference, the bending will be less. That means the light ray will not bend that much here. How much the light ray bends, that much here it will not bend. So see here, this is the first case and this is the second case. When the light passes through the lens, here the refractive index, different refractive indices. In the first case, it is more. So the bending will be more. That means the focal length will be more. And in the second case, the focal length will be greater than f1. Okay. Suppose in the first case, focal length is what he said, f1 is equal to 10 centimeters he gave. Am I right? So in this case, f2 is equal to approximately we will take 15 centimeters. If f2 is 15 centimeters, what happens to this one? 1 by, we know, no, 1 by f is equal to 1 by f is equal to 1 by d naught plus 1 by di. Am I right? So suppose if this is 15 centimeters and this is 10 centimeters, then what is di? So from this we can calculate now 1 by di is equal to 1 by 10. Am I right? In the first case it is 10 now. 1 by 10 minus 1 by 15. So this is how much it is? 10, 15 no. This is more. Am I right? So 10, 15. So we will take this one 2, 3. This is 30. And then this is 10 means this is 3 minus 2 that is equal to 1 by 30. And then di is equal to 30 centimeters. That means it will be farther from the bottom of the pool. Suppose earlier it is 40 centimeters. Now it will be 50 centimeters from the source. That is what he is asking. Am I right? So see this one. The index of refraction of material is greater than that of water, but less than that of lens. Then um, uh, uh, if describe the effect on the image and its position in each of the following cases. So we have to image how far it falls. It forms at a greater distance, and then the image will be of the same nature. Okay, the nature will not change, but only thing is the distance will change. That's all. Okay, so here you have to you have the clear understanding of the refraction. If you know the refraction of light theory, then it is very easy to answer the question. Okay. Hope this helps. Thank you. Bye bye.